Hi, everyone. Welcome to our webinar, How to Achieve 1 Million Records per Second in Kafka Ingest Without Sacrificing Query Latency. We're really excited about this one today, so thank you for joining us. I am Erica Fowler. I'm Senior Product Marketing Manager for Molecula. I have been in analytics for about 13 years, and I have worked in multiple industries, and I also have a PhD in epidemiology, where I've discovered my love of data and analytics. I'm here with my colleague, Garrett Roska, lead sales engineer for Molecula. Would you like to introduce yourself?
Sure. Hello, everyone. As Erica said, name is Garrett Roska. I currently lead our sales engineering team here at Molecula. I've been here for around 2 years and have a background in data analytics with a classical engineering degree that I'm now applying to all the fun stuff we're doing here. So pleasure to see you all, and thank you for joining.
Thanks, Garrett. Before we get started, we'd like to introduce you to our company, Molecula. Molecula is a technology company that closes the gap between data and decision, enabling organizations to unlock the power of real-time analytics and AI. Molecula is the creator of FeatureBase, the ultra-low latency database at any scale. So FeatureBase revolutionizes traditional tabular and columnar databases by storing data in a highly optimized format that achieves incredible compression ratios and still allows for really, really fast queries. More importantly, it sits on top of a conventional data model, such as like a relational star schema, data lakes, or streaming tools like Kafka, which we'll be talking about in depth today. And you can maintain up to the millisecond data updates and have practically no data preparation. So really excited today. We're going to show you some really cool stuff here. So on the agenda, we have, we're going to level set and talk about the rise of real time and how having streaming data doesn't necessarily mean that you can analyze it. Then we're going to go into a live demo so you can see FeatureBase in action. And then we're going to wrap up with a Q&A and discussion with the Molecula team. So Garrett and I will be talking to you and answering your questions. And we'll get to as many questions as we can during our time today. So just drop your questions in the question queue and we'll get to those during the discussion section. If we do not get to your question, don't worry, we will follow up by email after the webinar. All right, so first, the rise of real-time data. So the world is moving to always on, and real-time is not really an option anymore. Like if you're in the data and analytics space, like real-time is everywhere, it's expected. And even though Kafka and other streaming technologies have come in and made streaming data something that's accessible to organizations, they're still having a really difficult time having a unified view of their historical and their streaming data. So the older days of batch processing are still in play, even though we have all of these nice like real-time streams. It's really, really difficult to unify that data with historical data and actually make it useful. Garrett, anything you want to add to that?
Sure. So I think it'd be helpful to level set on, what batch processing means to us here at Molecula, what is data streaming, et cetera. So for batch processing, we consider anything where data is coming in, being collected in a sink of locations. So this could be an S3 bucket. This could be your batching up CSV files. They're put through some type of nightly process, maybe a couple hours, couple days, couple weeks. And then finally, it's propagated to your data store, and that could be any of the existing solutions we see in this space. So when we're looking at batch processing, we see this quite often with customers who are needing to add many different disparate data sets into a single view or do some type of large aggregations nightly. So these are the types of batch processing that we're referring to. With regard to streaming, specifically for Kafka, that means data is generated, let's call it in a web session or in some capture point. It is being piped through Kafka and then into a data store and then actually being queried live with results. So from source to sink is very contiguous. There's not a point in there where there's a long delay or a team is having to sit and monitor and do manual work on a given point. And that's what general streaming means to us.
Awesome, thank you. All right, next, Garrett, you want to give an overview of maximizing data ingest with minimal effort and how we do it here?
Absolutely. So what you're looking at is just a simple graphic. Before we dive in too much on this one, let's talk generally about our relationship with Kafka. So Kafka just happens to be one of the better streaming applications that we use here for Molecular and FeatureBase. We are not relegated to just using Kafka. We do see this with Kinesis and other types of streaming applications, but Kafka seems to be very one of the best. Now, with regard to what we're looking at here, if you're familiar with Kafka, which many of you are who are joining this webinar, you're likely used to taking in messages, producing them through the typical main mechanisms of Kafka, and then down through into a topic and then into consumers. So what I wanted to point out is that we made great efforts not to alter the process you see here. Anything above the light blue box is typically out-of-box Kafka. It's the most recent RPM package available on the Kafka site, downloaded to EC2 instances and deployed. Now, we haven't altered any of its structure. We haven't introduced custom JavaScript to any part of this. What we have done and how we maximize Kafka here at Molecular is in leveraging its unique ability to partition and sort messages into specific partitions for topics, and then consume from those partitions at a very parallel way. So that's how we obtain really high rates without really altering Kafka dramatically to achieve them.
So I know we've talked about, a lot of people can achieve really high ingest rates, like a lot of organizations do, but the engineers have to spend a lot of time like hijacking the process. So what's the impact of that on the team, or maybe the impact of not having to do that?
Sure, so that is correct. We see a lot of companies spend a good amount of time either creating very complex brokering systems or altering Kafka's innate pull mechanism to push records into its buffers. So there's a lot of things you can do under the hood to tweak and really fine tune this, but a lot of times we see data engineers or companies spend time on that part of the pipeline, but the other side is everything that you put into that you have to maintain, and then also downstream, how can you handle those rates? Is your data store prepared to handle millions of records coming through in a given time period? Are you having deadlock contention issues? So it just introduces a lot of problematic scenarios when you're starting to really ramp this up and scale.
And I think that theme kind of goes across a lot of different experiences I've had, not just with Kafka or like this specific scenario, but within like data operations and analytics in general. There's always a lot of effort to get things up and running, but a lot of times failure to realize how much effort that's going to take every day after launch to keep it going and keep maintaining it. So anytime something breaks upstream, there's like a fire to figure out where it is and to fix it. And it can be, the more complicated it is, the more risk there is in the maintenance phase. And then if there's ever an update needed or whatever. So definitely don't discount the maintenance phase of all these monster engineering products that are being built.
Absolutely. And just before we move off of this slide, one thing that I've missed in educating everyone who's joined is exactly how we are utilizing this pipeline. So just a couple of minutes. What we're doing is from the pool of records coming in, we are knowing where that record will live within FeatureBase itself further downstream. We are taking that knowledge and the hash that's associated there and moving it up in our stream. So we are essentially appending the product, which you see here in that little yellow box. We're adding a partition key, and that's telling Kafka to sort it into a specific partition from which we will consume from in a very specific manner. So that's how we're leveraging this little pipeline you see here. Now we can get forward.
Awesome, thank you. So how do we do this, and how is it different than other people are approaching using Kafka?
Sure, I would say with regards to Kafka, we keep it out of box as much as possible. We try not to alter it too dramatically, number one, but how are we able to sustain these rates? It's a mixture of many things, but predominantly it's our ability to both read and write at a very fast rate without introducing a lot of deadlock or contention scenarios. We do that with a couple of different methods, but the main one being multi-version concurrency control, which is, you can search this on your own. It's a very common method, but essentially allows us to provide a request or somebody trying to read from the data store, a snapshot in that moment. And then while that is being read, we can actually be writing to a new page. And then as soon as that is relinquished, that page is committed, and so on and so forth. So it allows us to sustain high rates of ingest through Kafka or other sources for that matter, while users are reading from our data store at a very fast rate. And of course, we can maximize the parallelism that Kafka can afford by being able to read from many different partitions or many different sources all at the same time without introducing a lot of errors in a very durable way.
Awesome. All right, so how is it that FeatureBase can handle 1 million records per second ingest?
Sure, and again, going back to it, it's the ability to spin up many different consumers, but mainly there's two things. We can separate out our ingestion cluster from our core cluster, allowing you to elastically scale your ingest side without introducing issues on the query side. For today's demonstration, we're actually running this all together, which we don't recommend for production environments, but for this exercise, it makes sense. But again, we can handle these records or this type of high ingest rate because we can decouple those infrastructures without having them tightly bound. Then we can maximize the parallelism we can capture from Kafka pushing all these records to specific partitions, us spinning up the requisite number of consumers and pulling those all at the same time. And this is all without introducing any type of downstream issues, which you commonly see with today's stores. Either they struggle getting the rate or they struggle inserting the data into their data store at a fast enough rate while not disrupting the ability for users to read that information.
Awesome. So I think that one of the things that we talk about a lot are trade-offs that you have to make, and the trade-off between the high throughput ingestion and the low latency querying. Like if you don't have a system like this that decouples the resources using those, then can you tell me about maybe like what are some of the trade-offs that companies or organizations have to make if they're not able to decouple those?
Yeah, the main one is that we see large enterprises throwing just lots of infrastructure at it, right? You end up with a very high TCO cost for your current solutions because you're trying to build very large infrastructure to handle this on a what we see commonly in the solution space. So you can just end up racking up a very high bill trying to hit these with just today's solutions. The other trade-offs we see are you end up back in a batch style where you can write very quickly, but then your users are suffering with slower or longer latencies on things you're trying to do. It may minimize how fast you can update historical information. So there are considerations we see being made in these decisions.
That is a great lead-in. Wasn't planned or anything, huh? To our next slide. One of our customers, it's often helpful for me to kind of understand how something like this would apply in the real world before you like dig into all the details. So just introducing you to one of our customers that had exactly the issues that Garrett was just describing. It's a provider of technology-driven video advertising solutions. They're using FeatureBase to power their real-time insights based on user actions. They're getting a lot of data from different sources, but one that generates a whole lot of data, it's like a behavioral clickstream type data, is like automatic content recognition for like smart TVs or connected TVs and devices. So our client is using FeatureBase to handle really, really high throughput of the data and maintain low query latency without having to spend as much on the infrastructure and without having to sacrifice the freshness of their data. And in this space, even a few minutes of delay between when the data is created to when you're using it, sometimes it's too late for it to really be impactful. So Garrett, can you talk a little bit about, you know, a little bit more about the results that they've seen using FeatureBase versus other technology that they've looked at?
Absolutely. So with this particular customer, the first, let's call it really good value we provided was we dramatically reduced the infrastructure that's required to keep up with this type of rate. So down from 1,000 nodes in Hadoop cluster down to just 9 nodes in a feature-based cluster, right? Now, outside of that, it's what they're really trying to do, and where this technology is most applicable is you have this high ingest rate, but really this data doesn't have an intrinsic value until you start applying some type of query pattern to it that can help some type of decision or some downstream constituent, a customer of yours, et cetera. So for this particular instance, they needed the ability to ingest very rapidly while also maintaining a very fast query pattern, right? And so going back to the trade-offs, we see companies either trying to push data in and then allow the aggregation process to run nightly so that they can actually query it. Well, what's the point of that, right? So in this instance, and this does apply to use cases outside of just this type of advertising, right? Where we're seeing a high clip of information coming in. This does apply to healthcare, IoT space. We see IoT device generation becoming one of the more prominent with the amount of data they're sending in, and they need to send it in for, let's call for predictive maintenance. Very similar. They need to take a lot of information in streaming. You need to have a query pattern that can recognize anomalous behavior and make decisions very rapidly. So we see the proliferation of this type of streaming necessity starting to touch more industries and just more common data pipelines.
Absolutely. I know most of my experiences has been in healthcare, and you know they've relied on claims data for so long. And while it's a huge volume of data, it's really messy and you know difficult to wrangle. It hasn't been real time. You know, there's like a 90-day run out period for a claim, and then you get it in batches from you know a payer or something, and you're having to analyze it, but there hasn't been that real-time nature. Well, now you have the wearable devices, so the IoT stuff is coming into healthcare, and we're actually being able to use those devices, and we've talked about it for a long time, but also electronic health records. There's been a really massive push to standardize how different systems connect so that all of this wealth of data that we have that isn't claims data with all the flaws that it has can be very helpful, but has a lot of flaws, can be used to to really do a lot more and really deliver on the promise of big data in these industries that historically haven't been able to capitalize on that. You mentioned one thing that's really that I think of, I may get this term wrong, but upserting on the fly.
Oh, yeah.
Can you maybe tell me a little bit about how that applies here?
Absolutely. So you made a good point when you said there's more information available to companies in disparate matters, right? So not only are companies providing themselves with their own first-party data, the data they generate from themselves, their customers, their applications, et cetera, they also have a lot more access to data that can be purchased on the open market, that can be provided by third parties. And we see a lot more industries creating these relationships to pull more data together. So now you even have more that you need to stream. Now, often introduces situations where you either need to enrich a data set or update, and we've heard this be called a couple of different things. Upsert is one, we've heard it be called inserting to existing, et cetera. But that means having an existing table or some type of data set, and then based on whatever key you have, updating all those records with new attributes, new information, right? And that can be very challenging in some of the solutions we see out there just due to the way that data is formatted and stored. For us, and here at Molecular FeatureBase, we can actually do that very easily and very quickly. So we have existing tables, and I need to enrich either people information, customer information. I can ingest to those at the same rate that I can in creating those tables, right? Which can provide you a lot of flexibility in data modeling and how you orchestrate and develop your query patterns against these. So it provides the ability to do that very quickly. So
Yeah,
does that answer your question?
Absolutely. It's a great description of one of the many reasons that I chose to join Molecular. The ability to do that is a really great, you know, special like superpower that we have here, and something we're really excited about. So if you're ready, without further ado, we can get into this demo.
Yeah, absolutely. So if you pass
Oh, yeah,
over
bear with me
control,
while
oh yeah, it's
I hang on just a sec. And I always forget how to do this. Sorry.
it's all right.
Here,
All right, so
did I do it? Okay.
you good to go? And let me share my screen. All right, so let me verify that you can see, in fact, this rotating cursor. Good to go. Okay. So you see a lot up on the screen at the moment. We're going to go through a couple of sections to make sure that we all have a good understanding of what I'm going to be showing you, what the data looks like, and all of that. So let's jump in and start with what does this data that we're going to be working with look like? So here in the bottom left-hand corner, you'll see we have a simple JSON message file that we generated. And what it has is two key value pairs. We have an identifier, which is alphanumeric. This is very common. We see this in the form of UUIDs. We see this in patient IDs, some kind of unique key that you're using to give meaning to here's the uniqueness of this particular record. Underneath this, we are capturing groups and ID arrays, which are just int arrays. And basically what this does is say, all right, this identifier belongs to this group, right? It allows us to check very rapidly. You see this type of data pattern in advertising. You see this in healthcare when you're adding cohorts of patients to specific diagnoses. So you see this very general data shape quite often throughout many different data sets. So for today, we've generated 40 million of these. And these are all unique individual messages, and each have an array. The longest array is out to around 1,000 particular groups, and this does decay in a logarithmic fashion. So if you were to look at all 40 million records across the spectrum, you would see some have many groups attached to them, and then all the way down to a long tail. And again, this is a very common data shape we see in the space for Facebook-like pages. Very common to have many records that have a lot of attributes, and then all the way down to a few. So that actually gives you an idea of the shape of data we'll be ingesting into a table. While we're doing this, here the unique part we're going to be looking at is maintaining query latency while we ingest at a very, very high rate. So in the background, we are running this entire setup on AWS in a cluster of 3 nodes. And everything is running on those nodes. So Kafka is running on the same nodes we'll be ingesting to, using the same compute. And we also have JMeter and Grafana on this as well, and we'll be looking at some of these dashboards. So
you mentioned, sorry.
No,
you mentioned everything's running on the same cluster, but in a production environment, that wouldn't necessarily be how this is set up. Can you maybe explain that again?
Yeah, absolutely. So just for the purpose of this exercise, it made sense for us to try to pack as much as we could onto a very minimal infrastructure, just due to our CFO's heart. But mainly in production, we would advise you to split these out. You would, in production environments, you typically have your own Kafka cluster, your own broker set up there to handle all the records and orchestrate as you see fit. Then you would have an ingest cluster and maybe some, usually around 1 machine for that for most of ours, and then your core query cluster for FeatureBase that's replicated and all that good stuff. So production, you would want to split your infrastructure out for many reasons other than the obvious.
Thank you.
Great question. All right, so let's talk about, so again, running all on the same machine. We have JMeter running. JMeter is simulating 25 concurrent users all at the same time, sending requests to the cluster, right? So we are simulating as if people are logging in and running an assortment of queries. Some of them are, the 4 main ones are listed here. So we'll be running a select count distinct from all the groups. The maximum, the cardinality of the groups is typically around, in this data set, is 26,000 unique groups. So as the records are flowing in, we'll be querying more and more as time goes on and getting the distinct count across that. We see this query very often in almost every use case, because you're looking for distinct elements about given record sets. You're looking for distinct counts for various reasons. The next two are, let's call them a little bit more just general complex queries, which are introducing and or statements. So you want to find everything that matches this and that or this, and we have those flips just to show a little bit of let's call it some breadth there. And then the last one is a top K. That's sort of a special query that we run here in Molecular FeatureBase, and it really leverages our technology to the maximum and can produce very rapid and accurate counts across billions of records. So we do that in there. You'll notice it's the only one that's not in traditional SQL, that is in our DSL PQL. So what we'll see is behind the scenes, we have this Grafana dashboard running each of and just tracking each of those queries from the endpoints we make available. And we'll be looking at the max and average of these queries, of all of them, of each of the distinct ones. And then we threw in pinging our web UI that's available out of box with our system as well. So that gives you an idea of what we'll be looking at, the data shape. Now let's move over to setting up Kafka. So what I've run here is just a quick look at the topic itself. What we've done is we set up Kafka with a single broker, nothing complicated. And we have created one topic called segment 64, and we split that topic into 64 partitions. Now, as you can see here, running that this describe console command will give you here all the partitions that you can see all the way down to 63. And this is what we'll be populating. Now, on the other side of the house, we have our Molecular IDK out of box, comes with a static consumer, and we are going to run that in concurrency 64, the batch size of 262,000. So what that is going to do is we're going to grab the file we created, use our producer to push that file in, and just one more matter of, let's go back to this for a second. Hold with me, this one. All right, if you'll notice at the very beginning of these records, there's a little number here, and that is a pre-appended key. Now, just a reminder, what we're doing here is we know based on this identifier where this record will live within FeatureBase. So we are grabbing that hash, moving it up into a ETL process, which you can commonly do in many tools, and essentially pre-append this record. Now, when this producer is pushing this this file into our Kafka topic, it is using that comma as a key separator, right? So essentially, we're telling the producer, you need to grab this record and push it to this specific partition. And then on the other side, we'll have our consumer looking at a specific partition, grabbing it and introducing that into the FeatureBase store. So that is the start to finish of how we can key it, show you where it's going to go, and push it in very rapidly. Does that make sense, Eric? Any questions so far? Did I miss anything? All right, good. So let's go ahead and pick this off. So what I'm doing here is I'm grabbing that JSON file, 40 million records shaped on the bottom left here, and I am populating the topic and all the partitions. So it's going to take around 35 to 40 seconds to complete. While that finishes up, on the other side, we're going to run the command to start ingesting into FeatureBase here in just a moment. We are going to create a segments table. We're going to run 64 of these concurrently. So when I kick this off, it will spawn 64 child routines. All right, and that's completed. So that means that our topic is fully populated and we can pull as fast as we can from Kafka. So
you said that was 40 million records, and it was that fast.
Well, that loaded up into topic ready to be pulled.
Okay.
Right? So we basically don't want to limit our ability to pull based on how fast Kafka can get into memory. We are going to have that pull ready to go, and we're going to pull as fast as we can into FeatureBase. So now when I kick this off, what we're going to be looking at is here, this is updating at a 5-second rate. So these queries are running live right now. So users are running, but there's no table, right? So it's going to be fairly flat, right? That's why these are coming back with 3 milliseconds, right? It's just the requests aren't processing. Now, as soon as our tables start to populate, we'll start to watch these trends go. So we're going to be watching live ingest and live query. So let's kick that off. The first thing you'll notice is it's going ahead and creating the schema based on the ID and those groups. And here in just a moment, after all the child routines have done spawn, we can start to see them translating and importing those batches. Now, immediately, you'll see at the bottom here, the queries start to, query transaction time start to go up in rate. So again, we're running 25 users, all randomly choosing one of those queries every second and populating it, right? Now, we're going through. I captured the timing where this run will take just over 66 seconds and we'll ingest all 40 million. But again, you can see that so far our max time is still coming in around all of them are still taking 2 and 58 milliseconds across all 25 users at the max rate, which is pretty fantastic for ingesting and running the same cluster. And you can see that we've already started to maintain a steady state. So we're starting to dip back as those queries are running. And we're just about to finish up here. And you can see the imports batches are starting to time out. Really the only downside of what we're doing here is that we're relying on parallelism to maintain our rates, right? So what we're gonna see is a spike in rate over 1 million, and then it's gonna slowly go down as the consumers exhaust their particular partitions, right? We don't have it set up to where a consumer can go and grab a different batch if he runs out in his partition. So we're gonna see a nominal rate, and that's already done. So that took 68 seconds. That's roughly 588,000 average records per second. But remember, as you can see in here, as these start at the timeout, we're losing parallelism, right? So across the 64. So we probably hit a peak rate just around 1.1-ish million at the beginning, and then that pattern slowly degraded as consumers ran out. And as you can see, now the table's populated, these are starting to level out more consistently because we're not ingesting into that table at the moment. But our max rates came in around 180 milliseconds, this is the intersections. So this is a complex and or looking through every record in there, 40 million record query. And the averages are well in the 30 milliseconds, 61 milliseconds, even the count distinct are coming in 60 milliseconds, which that's a very expensive query on traditional systems. So
I may have been yelled at a few times for trying to use count distinct too often in a SQL server.
Yeah. So again, we're ingesting into a table that already had a few records in it. I could rerun, or I could continue to stream into this one, but for this exercise, we just wanted to show, again, a very high rate, a sustained rate coming in, 40 million records. And let's take a quick look at our web UI just for a moment. And in here, I'm going to refresh, and you can see our tables populated. And if I come in here and do a count all, you can in fact see we're 39,399,997 records in that table. So just to let you know, in fact, we did ingest that data. It's live. This is the web UI that's being pinged in this homepage query right here. So that would conclude it. We've just ingested 40 million records. Our query times were sustained at a very good rate for that number of users on a very small cluster of the size. So.
Thank you. This is really exciting to see, and I love the visualization of the queries and the concurrent simulation that you have. Couple of questions before we dive into the Q&A. Just like in general, like why should people care about this? Like why is this so cool to us?
Well, number one is the ability to ingest this data and capture very fast state changes in the underlying knowledge base, right? So this could be your consumer's behavior. This could be some applications you have that are running. This could be IoT devices that could have a critical error that you need to see. We often see this in fraud detection, anomalous behavior, et cetera. So this ability allows you to take in data at a very high rate and be looking for this at the same time, right? Which can be very challenging, especially as you have more and more processes consuming from these tables, right? So again, this is 25 users. We have cases where we have a program or a top layer client sending hundreds of queries in a very fast pattern. So this is stimulating users. We're moving towards applications that can pull this at a very fast rate. So now you're really capturing very discrete, very granular views of things that are occurring out in your system.
Yeah, I think that's something that like the machine-to-machine interactions and the level of concurrency that's needed in those situations is a little bit different thing to wrap your head around when you're talking about like query latency and what that means.
Absolutely.
For business. All right, we can dive into the Q&A now.
Great.
All right, let's see. All right, so here's one. It's like, okay, that was really fast. And have you seen this be challenging in other data stores, and why?
Yes, I would say we've seen it be challenging. One, again, due to the resources required. Some data stores require just more nodes to be able to handle that ingest rate. But mainly, I would say we see this when companies or organizations are trying to ingest into already existing data sets, right? So that they have a historical table and they want to enrich that historical table, remove the necessity to do joins. And so they're trying to add attributes, add new data to an existing platform. And that can be very challenging depending on what solution you have. If you have like Elasticsearch and a document style, it can be difficult to go document by document for updating a large swath of them at a given moment. We see this in schemaless databases where, for example, Mongo, where they're pushing data in at a very high rate, but then you're just pushing your compute onto the backside, so your queries are a little slower. So it can be challenging just to maintain these rates consistently, update information without disrupting or introducing a lot of fault areas in a large infrastructure.
And you mentioned this earlier with one of our customer stories, like the hardware reduction, like can be really significant. You mentioned going from like 1,000 Hadoop servers to 9 FeatureBase. So we're not talking like a small amount of savings here. Like it's a game changer.
Yeah, and in many organizations, we can make a significant impact on the TCO behavior because we know the world is moving towards, or many organizations are moving towards cloud. They're moving towards either their own VPCs deployed within larger ones like AWS, GCP, Azure, for example. But they make it very easy to spin up infrastructure to do a lot of stuff, but with that comes a very hefty bill. And so some of these, let's call it infrastructure hungry applications, can make it very challenging for executives and business decisions to kind of orchestrate what value they're getting from their data sets and how are they maintaining those.
All right, let's see. Can you achieve rates like this with other types of data and not just Kafka?
Yes. For batch, we do have customers who still do batch, right? And there's sometimes good reasons for that. Let's say they have streaming and they only get batch information from purchased data sets, for example, right? So you want to sustain the same ingestion rates and get that data in quickly. We can do that from CSVs, other SQL tables, those that have ODBC connections out to other data stores. And it really becomes just a matter of how fast can the disk provide that information to us. Typically, we become IO bound, right? Because we're trying to read it very rapidly. It's not a compute issue where we're having to offset memory or compute on the FeatureBase side. So the answer to that question is yes. We can take it in from other sources, other streaming tools. In fact, like I mentioned, Kinesis is our choice for our SaaS product, and other CDC or change data capture tools as well.
All right, thank you. And then I think we've covered this. This is maybe worded just a little bit differently. But it's a little bit different version of the question. But why can't other companies or solutions do this the way that FeatureBase does?
Oh, so that goes on a very deep level. It goes through our feature first format, the way that we are decoupling the data from a traditional relational or columnar store, which is most used in all the solutions we see today, right? We actually have a proprietary format that we're converting the data into features, and that allows us to store it in a specific way and also update it in a specific way. So it's due to that underlying format. And then of course, we do have on top of this etcd managing our cluster, so we can cluster and we shard automatically. So let's call it intelligently distribute the features as they come in. So it allows us to, one, parallelize many operations on ingest and query, but also allows us to translate that data and then update it very quickly, because we're not having to represent those elements over and over again as you would in, let's say, a columnar store.
All right, thank you.
These are great questions.
Yeah, definitely. So I think that that we're out of time for questions today, but don't worry, if you have a question, put it in the question queue, and we will follow up with you. If you want to learn more about FeatureBase and how it could impact your organization more specifically, please reach out. You can go to our website and contact us there. You can request a demo or go through the contact us page. We're happy to talk to you about what this might look like with the specific use case for you. Everybody's data is different, everybody's situation, the problems that they're trying to solve are often really different, and we have a really great team that can help walk you through what that might mean for you. We're, excited that you joined us today, and hope that you learned something new, and yeah, can't wait to see you at the next one.
Yeah, and thank you to everyone who attended. If your question did make it in, please do submit those. Myself and my team will get answers out to you. We're eager to hear from the community. So again, thank you for joining and appreciate your time.